All right, so welcome back. We're starting a new unit on something called rotational dynamics. We've already looked at kinematics in a few different ways. For example, we looked at one-dimensional kinematics, and we got used to the idea of displacements and velocities and accelerations. And then we took that idea and we moved it into two dimensions, where we looked at projectiles and looked at how perpendicular vectors are independent from one another and act independently. If we want to properly describe how things move in circles, or if an object is rotating, how it behaves, then we have to look at this idea of rotational dynamics. So just before we get started here, I want to ask you a quick question. Suppose I've got four objects on a ramp, and they're all on the same incline ramp, and let's say for the sake of argument they all have the exact same mass. And there's only just enough friction so that these objects all roll. They don't slide down the hill, they're going to roll. But the four objects are different. There's the green one is a spherical shell, so like a basketball where all the mass is on the outside. The red one is a solid sphere, so maybe like a pool ball. The ring, the blue one is a ring, so a cylindrical shell, and then the gold one there is a solid cylinder, so it's like a can of tuna. And again, for the sake of purposes, let's assume they all have the same radius. Now, if I let this go and I ask you which one is going to win the race, I would expect many of you would predict, well, I think it's going to be a tie. What you might be surprised to learn, though, is that when we in fact run this, despite the fact they have the same mass, the same radius, they finish the race in much different times. So, for example, it looks like that sphere wins pretty handily, just ahead of the cylinder, and the ring is just way behind. And so the question should be, well, why is that? I mean, what is it about these different shapes that causes them to move down the ramp at different rates? If we want to do that as a comparison, if I add a block of ice here that's just going to slide, so a frictionless cube is just going to run down this ramp. If I run those against that cube, well, the cube wins the whole race hands down, no problem. So something about those shapes and something about the fact that they're rolling and rotating seems to be changing their behavior. And it's really about the shape themselves, not the mass, not the radius, but that where the mass is distributed. So we're going to look at a few different ideas here. The first one I want to introduce to you is this idea of rotational angle. Okay, so if we have an object like a CD, which is a compact disc for you children out there, if a CD is spinning around, then you could describe the motion of that CD as it's spinning by talking about the rotational angle, which is basically just the amount of rotation. And what we're going to see over and over again when we compare rotational dynamics to linear dynamics is that there's going to be parallels. So, for example, how far an object rotates, the angle that it rotates through, is really going to be analogous to the linear distance that an object traveled. If you're thinking about one-dimensional kinematics, like displacement and velocity and acceleration, the angle that you rotate through is going to be analogous to the linear distance. So we define the rotational angle, we just call it theta, and it's just the ratio of the arc length to the radius of curvature. So basically, you may have learned this in your math classes, that if you have a circle of a given radius and it travels through an arc length here, so it's got an arc length, the arc length being the distance that it travels on the outer edge of the circle. So you can imagine a single point here on the edge of the CD and it traveling a certain distance. That would be your arc length. And so the change in your angle here is just going to be the change in your arc length divided by the radius, where this is our rotational angle. And this is measured in radians, and more on that in a second. Arc length is S, and R is our radius. So it's worth pointing out that for a given circle, if you were to travel all the way around the circle, you would have completed one revolution. If you haven't seen this idea of radians, radians is a way of basically of measuring angles, but instead of using degrees, we're going to use radians. And what we say is that if you imagine a circle that had a radius of 1, affectionately called the unit circle, and you imagine traveling all the way around outside that circle, doing one complete loop of that circle, you might ask, how far have you traveled? Well, if the radius is 1 and the circumference is 2 pi r, then you would have traveled 2 pi. And so this is how we kind of define our radians. We say that 2 pi radians, or rad, is equal to 1 revolution. So you could say that that's also equal to 360 degrees. So for example, if you did a 180 degree rotation, that would just be pi radians. And so you're going to have to be able to convert between between radians and degrees. So if the rotational angle, it gives us an idea of how far the object has rotated, the displacement, if you will, then the angular velocity gives us a measure of how fast. And so the symbol for angular velocity is omega, which just looks like a fancy W. And it's just the measure of the rate of change of the rotational angle. So how quickly the rotational angle is changing. Now, just for a conceptual look here, let's take a look at something here. So imagine I've got two circles, and I've got these objects at the end of the circle. Now imagine that the second circle is much bigger than the first, okay? But when I turn it on here, both of these circles move around. Both these points, these red points, move around the individual circles with the same frequency, which is to say they take the same amount of time to complete a loop or a cycle. Now, when you look at this, it's pretty obvious that the red dot over here on the right, this red dot is traveling much faster than that red dot because it travels a much bigger distance in the same amount of time. Now, imagine that these weren't two separate objects. Imagine that they were actually the same. Like imagine that you had a merry-go-round or even a CD spinning. If you tried to describe the motion of how fast this CD is spinning, you'd run into a big problem because the question would be, well, how fast is what part of it spinning? If you look on the very outer edge, the CD is spinning very quickly. If you look down closer to the center, the CD isn't moving nearly as fast. So how fast something's spinning, it's not really useful to describe it in terms of regular velocity, in terms of meters per second. And so instead, what we talk about is, okay, well, how many radians per second is it going through? Notice how both the outer edge and the inner edge, doesn't matter how close we get to the center of the circle, they both have the same angular velocity, which is to say they both travel through the same number of radians in the same amount of time. And so when we talk about rotating objects, we're going to have to talk about rotational angle instead of displacement, angular velocity instead of velocity. And so we define our angular velocity as our change in rotational angle over time. But remember that we just learned back here that the rotational angle is delta S over R. So we could say that this is equal to delta S over R times t. Well, if you think about it, S over t, which is distance over time, or displacement over time, that's really just velocity. So since velocity is just displacement over time, then I can substitute this in here and I get velocity over radius. So long story short, the angular velocity is just equal to the velocity divided by the outer radius. Or I should say, the angular velocity is equal to the velocity of a point on the outer edge divided by that radius. And so the units for angular velocity are radians per second. Okay, let's do a quick example. So calculate the velocity of the angular velocity, of a 0.3 meter radius car tire when the car travels at about 54 kilometers an hour. So first thing we're going to do is I have no use for kilometers an hour, divide by 3.6, and that'll be right around 15 meters per second. I know that my angular velocity is equal to the velocity of a point on the outer edge of the tire divided by the radius. If it's traveling at 15 meters per second, and then the radius is 0.300 meters, that's going to give me 50, and then rads per second. Now, it's worth pointing out, if you look closely here, radians are kind of this funny unit. They're a bit of a phantom unit. They sort of disappear when we don't want them there, and then they show up when we need them. So if you look at the units, meters per second divided by meters, the meters cancel out. You might look at that and say, well, that should just be in per seconds or even hertz. But as a matter of fact, since it is a velocity, an angular velocity, it's going to be radians per second. We didn't include radians in here. And so I should point out that what we're talking about here is we're taking the linear velocity or linear speed of the car, how fast the car is traveling in the forward direction, and we're translating that to how quickly the tires must be rotating. Of course, the distance traveled by the car in one rotation is equal to the circumference of the car tire. So if the car tire rolls one complete rotation, then that would equal the linear distance traveled. So what would the angular velocity be for a car traveling at the same speed but that had tires which were 4 times larger? So how quickly would the tires have to rotate if the tires were 4 times bigger? So just think about that for a second. Would the tires have to spin faster or slower? Would they have to complete more or fewer revolutions per second? And so since we know that omega, the angular velocity, is velocity divided by r, then we know that omega is proportional to 1 over r. If we have the same speed, then I'm not really worried about that v. And so you could say something like, well, if omega 1 is v1 over r1, and that equals 50 radians per second, then the new omega, omega 2, would just be v1 over r1 divided by 4. And so that would be 12.5 radians per second because of the proportionality. Okay, well, we've looked at rotational angle, which is like displacement. We've looked at angular velocity, which is like linear velocity. And so now, of course, we're going to look at angular acceleration. So in previous unit, we looked at uniform circular motion. So keep in mind, with uniform circular motion, the whole time we assumed the motion was uniform, which is that to say that it wasn't accelerating. Well, I should say it wasn't speeding up or slowing down. The speed was staying constant. And so with angular acceleration, we're talking about a situation where not only is something rotating or moving in a circle, but it's also speeding up. So you could imagine like a merry-go-round ride that's not moving yet, and then it slowly starts to speed up faster and faster and faster. So the symbol for angular acceleration is alpha, and we define it as the rate of change of the angular velocity. And so alpha is just the change in omega over time. And you can imagine here the units would just be radians per second squared. Okay, so we'll do a couple of examples. Suppose a Rockbridge student puts their bicycle on a stand and starts the rear wheel spinning from rest to a final angular velocity of 250 RPMs, or revolutions per minute, in 5 seconds. What is the angular acceleration in radians per second squared? Okay, well, this really is just more of a problem of converting our units. So we know that we've got 250 revolutions per minute. Okay, that's what RPM stands for. Well, I know that there are 2 pi radians for every 1 revolution. And I know that there is 1 minute for every 60 seconds. And so if I look closely here, I can see that revolutions is going to cancel out, minutes is going to cancel out. And 250 revolutions per minute works out to be 26.18, if you want some sig figs, rads per second. Once I know that, then it's pretty straightforward to say, okay, well, my angular acceleration is my change in angular velocity divided by time. Change in is final minus initial, so 26.18 minus 0 divided by 5.0 seconds. And this is going to work out to be right around 5.2 radians per second squared. So suppose they now slam on the brakes and causing an angular acceleration of negative 87.3 rads per second squared. How long does it take the bike to stop? Well, again, angular acceleration is just going to be a change in angular velocity divided by time. And so time will just be my change in angular velocity divided by acceleration. Now I'm going from a final to a final angular velocity of 0. I started at 26.18 and I'm dividing that by a negative acceleration because it's slowing down. And this ends up being 0.30 seconds. So it's worth just pausing here for a second and just considering the relationship between circular motion and linear motion. So like I kind of hinted at before, we've already talked about things moving in circles. We've talked about satellites in orbit. We've talked about merry-go-rounds going around and people driving over in roller coasters going over hills and things like that. But what we sort of have, like I said before, what we sort of neglected at this point is we just assumed that everything was moving at a constant speed. And so what happens if you have something that's, yes, moving in a circle, but also speeding up? And things get a little bit complicated. So if an object experiences an angular acceleration, then the velocity of any point on the object must be increasing or decreasing. So the linear acceleration is tangent to the path of the rotation. And so then we'll use a slightly different symbol, A with a little t for tangent. So if you look at this diagram over here to kind of explain what's happening. So just ignore this arrow for a second. Suppose you've got an object that's spinning in a circle. Well, we all know the story here that there's going to be a force directed towards the center of the circle. And so that's going to be my centripetal acceleration is going to be inwards towards the center of the circle. We know that at that point, we've got a little point here on the outer edge of our circle, and that the velocity at that point is tangent to the circle. None of that is new. What we're saying now, though, is that if this object is also speeding up, so think about a merry-go-round that's not moving and it's slowly speeding up, getting faster and faster and faster. As it speeds up, it must also be accelerating in this direction here, and we call this a t. So the acceleration which keeps it in a circle is still centripetal acceleration. It's still this right here. It's still equal to v squared over r. Nothing's changed there. But on top of that, we could be causing this object to move faster and faster in a circle. And then it would have an acceleration, which you can see now is in the same direction as the velocity. Keep in mind that perpendicular vectors are independent. So this acceleration, the centripetal acceleration, could never change the speed of the object because they're perpendicular. But the linear acceleration here can. So the linear acceleration we're going to define as a change in velocity over time. But you remember that we talked about linear velocity. And we said that angular velocity is linear velocity divided by the radius. Or put another way, the linear velocity is the angular velocity times the radius. So I can substitute this into this expression here, and I get omega r over t. Well, we just defined omega r. We just defined our angular velocity. We just defined our angular acceleration as being the change in omega over t. And so you can see right here, that's exactly what I have. And so I can substitute this in here. And I end up with alpha r. So the linear acceleration of a point at the end of the circle is equal to the angular acceleration times the radius. Or just to reverse this all around, the angular acceleration is equal to the linear acceleration divided by the radius. Okay, so note again, it says here, note that the angular acceleration is tangent to the circle, whereas the centripetal acceleration points towards the center of the circle. Okay, so with all of this having been said, we've learned about angular rotational angle and how that's related to displacement. We've learned about angular velocity, how that's related to velocity. We've learned about angular acceleration, how that's related to acceleration. So now you're probably wondering, hey, We used to have some really fun formulas that we used to use for linear kinematics. I wonder if we can use those again. And the answer is you are in such luck that absolutely. All the same formulas that we had in translational or one-dimensional kinematics. So like your good friend V equals V naught plus AT, or D equals V naught T plus 1/2 AT squared, or V equals V naught T plus 2 AD. All of those have an analogy in the rotational world. Okay, so for example, V equals V naught plus AT, well, we could just say that omega equals omega naught plus alpha T. And so just keep in mind the kind of the analogy we keep using. So displacement, we think of displacement, the analogy to that is rotational angle. And velocity, the analogy there is angular velocity. And acceleration, the analogy there is angular acceleration. So if you look at each of these cases, you can see that we've just substituted in different versions, the analogous version of each variable. Okay, so let's put these to work. So a deep sea fisherman hooks a big fish that swims away from the boat, pulling the fish line from his fishing reel. The whole system is initially at rest, and the fishing line unwinds from the reel, which has a radius of 4.5 centimeters from its axis of rotation. The reel is given an angular acceleration of 110 rads per second squared for 2 seconds. What is the final angular velocity of the reel? Well, just like we would do with linear kinematics, let's set up our variables. We've got omega, omega naught, alpha, theta, and t. So all the new players. And so we know, for example, that it's initially at rest. So the initial angular velocity is 0. The angular acceleration is 110 rads per second. The time is 2 seconds. And so if I go back and look at my options here, of all these options, the one that's going to give me the final angular velocity of the reel is this one. Omega equals omega naught plus AT. Subbing in the values, we see the 0 plus 110 times 2. And so this is going to be 220 radians per second. All right, so at what speed is the fishing line leaving the reel after the 2 seconds elapses? So how fast, and think about that too, that the fishing line is on the outer edge of the reel. So if you think about the reel spinning, you think about a point at the edge of that reel spinning around, the fishing line is traveling at that same linear velocity. And so we could compare the way we sort of jump between angular and linear is through these formulas here. So angular velocity is linear velocity over radius. And so that's the speed at a point on the outer edge. So the velocity would equal the angular velocity times the radius, which is 220 times 0.045. Remember, that was in centimeters. And so 9.9 meters per second is how fast the line is actually coming off the reel. Okay, so how many revolutions does it make? The number of revolutions is going to depend on theta. And so if I look at my formulas here, which one could I use to solve for theta, knowing what I know? I've actually got 2 options, but I'll choose this one. Theta equals omega naught t plus 1/2 alpha t squared. This is, again, 0. So this simplifies to 1/2 times 110 times 2 squared. And so this is 220 radians. Now, just be careful there that it didn't actually ask us for radians. It's actually asking us for how many revolutions. And remember that 1 revolution is equal to 2 pi radians. So I can multiply this by a conversion factor here of 1 revolution for every 2 pi radians, and I get approximately 35 revolutions. Okay, and then last but not least, how many meters of fishing line came off the reel in this time? Again, the way we jump between linear, so this is a question, how many meters is asking a question of linear distance. How far did that fish swim away? And so the way we jump between those two is with these formulas, that the angular, rotational angle is equal to the arc length, or the distance traveled, divided by the radius. And so the arc length, which is equal to the linear distance, is equal to theta times r. So that's 220 times 0.045, which works out to be right around 9.9 meters. And that's just a fluke that it lined up with the earlier velocity. Don't look too much into that. Okay, that's it for the first part of rotational dynamics.